Are we good again? Awesome. All right, I'm just gonna wait another 30, 40 seconds just to see the number go back to where it was. We had 5 people before, so I'll just wait for the other people to join back again. In the meantime, I'll show you, yeah, definitely. Okay, so we're up to 3 people. I'm just gonna keep it going. Oh, 4, there you go. Number we were looking for. Okay, so, awesome. So now let's get back to where we're going. We had just gone over the heart, the thymus, the digestive tract, and now we finished the kidneys. And last but not least, the thing that we actually usually associate with hormones. These are your gonads. So gonads are going to be your sexual reproductive organs. Male and female reproductive organs will be secreting different hormones and have different hormones that affect their function. So the balance for these types of hormones are going to change your whole behavior, change your libido, change for women. Well, it will change during different parts of your menstrual cycle, or if you're on birth control, or if you are stressed out. Both males and females, you'll have a change in these sex hormones, as well as your sleep and all of these other things that we do on a day-to-day basis. These are all going to affect the functioning of our gonads and the levels of hormones that they produce. So now that we know the main glands, so the main ones again are the hypothalamus and the brain. We have, right? So there's like a pathway that connects them, and I'll just pull this up for you guys up on the camera. So as you guys can hopefully see, what I'm talking about over here is that you have your hypothalamus, and then you're going to have it be regulating this pituitary gland over here. And the way that it does is by connecting to the pituitary gland via this stalk. And the stalk is called the infundibulum. So the, once again, infundibulum. So that's going to have the connections for the synapses to pass through. And you also have a whole bunch of these arteries and veins that are kind of leading to the pituitary gland. And more important than the arteries are these veins, because they form a portal. So kind of how we said a plexus is a bundle of spinal nerves. Right now we're talking about these veins, and a bundle of veins is going to be a portal system. And why would it be important to secrete it into the veins? You would want it to then get back to the heart from where it is over here. It needs to travel down to the heart. And then from the heart, it's going to be pumped out to the rest of the body through your arteries. So it makes more sense to give it through the vein and just pump it out to the end of the extremity. It's a one-way system. So the veins are going to take it from the place of where we injected and actually bring it back to the heart, where it's going to go out everywhere. So that's a lot faster. Also, your veins will be able to distend or stretch to accommodate for the extra volume. Your arteries have smooth muscle in them, so they're not going to expand as much. Instead, they're doing more contractions. Okay. So now we know the organs, we know how they look like, where they are, and now we're going to get into what they're secreting, why they're secreting it, and how it helps to return to balance, right? So this is going to be the common theme. What I recommend for you guys to do is set up a table that's going to look where is it? Okay, so set up a table with the different hormones, like on each the hormone name, and then put where is it being secreted from, where is it being produced, and in response to which stimulus. Okay, and then lastly, its function. Because these are the things that you need to know about all of the hormones that we're going to be discussing today. So first of all, let's go through the different functional classes of these hormones. So based on what the hormone was made from, you're going to have different classifications. What I mean by that is that it's either going to be an amino acid derivative, or it's going to be a peptide hormone, or it's going to be a lipid derivative. So let's break down those words real quick. So if it is a amino acid derivative, that means that it's going to be a single amino acid. These types of hormones are sometimes called monoamines. So monoamine amino acids. So these are going to be a single amino acid hormone. So that's what we're talking about over there. And then you have your peptide hormones, where you have more than one amino acid put together. And again, it's a protein hormone. And then lastly, you have your lipid derivative hormone. This is going to be made out of fatty acid chains or from cholesterol. Lipids are fats. So you have your cholesterol and you have your amino acid and peptide hormones. These are the different classes. And let's go back to your amino acid derivatives. So they can either be, so some examples of these are going to be your thyroid hormones. So your thyroid hormone is made up of a single amino acid, and it's going to be produced by your thyroid gland. And one of these is thyroxine. The other one is going to be triiodo. It's T3. Where is this? Oh yeah, triiodothyronine. So T3 and T4. So your thyroid is going to be releasing these kinds of hormones. Then you have your catecholamines and you have your tryptophan derivatives. So these are going to be made up of a single amino acid that's then going to be manipulated to form this last type of hormone, the final one. Your peptide ones are similar to this, except you have more than one. And what these two have in common is that more likely than not, they're going to be hydrophilic, meaning that they can go into the extracellular matrix. They could go into the intracellular, where both of them are made up of water, hydrophilic on both sides, but they will not be able to cross the lipid bilayer, phospholipid bilayer, which is your membrane. So this is why your lipid derivatives can easily cross through, but your protein-based hormones will not have that same ability. Instead, they need to bind to a receptor on the cell membrane to trigger the action of in the target cell. Okay, so going back off of that, we have certain hormones that are direct, meaning that they're able to go directly to their target. And then we have ones that need to use secondary messengers. So these secondary messengers are going to be using G protein signaling. So I'm not going to get into that right now, but basically you have a protein that is being activated that causes this chain to start, and this cascade leads to the other hormone then becoming activated. I mean, the target cell becoming activated to do whatever it needs to do. And now, most of the time, the way that this activation is going to happen is that it enters the cell or targets a receptor that then causes something to enter the cell. And in both cases, what you end up with is your transcriptional regulation. So it's either going to cause upregulation or downregulation of your transcription of within your nucleus. So transcription is when you go from your DNA to your RNA, and then translation would be from the RNA to your proteins. So by increasing the number of times that you produce RNA, your transcription, you increase the proteins being produced, and therefore you will change your function through this cellular mechanism. Okay, so I'm going to skip over to the pituitary gland. So now we are on page 602, and you have this pituitary gland where you have 9 hormones being released. Earlier on, I said all others. So what I meant by that is that your anterior lobe of your pituitary gland is going to be releasing F for your follicle stimulating hormone, L for your luteinizing hormone, A for your adrenocorticotropic hormone. So your thyroid stimulating hormone, and then you are going to have PEG, prolactin, which is going to cause the stimulation for women to actually produce milk in their mammary glands. So this is important for breastfeeding. Also, the reason why some men will grow breasts. So then you have your PEG. So you have so I'm sorry, one second. You have your flat PEG. So you have your epinephrine, which is also going to be released, as well as your growth hormone. So your growth hormone is that G over there, and that would conclude your anterior. And now it's time for the posterior. So in the posterior, you have all others. You have antidiuretic hormone, or ADH, and then you have your oxytocin, others. So I'm going to type this out for you guys so that you are able to write this. So F is for follicle stimulating hormone, L for luteinizing hormone, A for adrenocorticotropic hormone, T for thyroid stimulating hormone, P for prolactin, E for endorphins, and G for growth hormone. Okay, and then for the all, A is for antidiuretic hormone, and O is for oxytocin. Okay, so that summarizes all of those. And so now you should have the names for each of the 9 hormones that are being released by your pituitary gland. And now what's interesting about this is that the direct hormones, meaning that the anterior hormones, if you notice in all of their names, it says stimulating or tropic hormones. And what that means is that it's stimulating something else to actually act. So it's not that it's doing it itself, but something else is doing it. So you guys want to keep track of these words. And now there's an in-depth description of each of these hormones and what they're doing. But before we get there, the last hormone that's being released from the pituitary gland that's not listed here is in between the anterior and posterior lobe. There's this grayish area right there, right? And so that grayish area that we're looking at, that's going to be your intermediate lobe. And the intermediate lobe is the one that's going to contain your melanin producing hormone. So your MSH, which is your melanocyte stimulating hormone. Intermediate. I was just on page 603, Matthew. Intermediate lobe secretes MSH. Melanocyte stimulating hormone. And melanocytes are the mature cells that are found in our skin that are going to secrete melanin, which gives us this pigment, darkens our skin, and allows us gives us some protection from the UV radiation of the sun. Okay, so you have, if you want to flip over to 605, you have this wonderful chart where you see all of the hormone names, where they're coming from, and where's their target. So we're going to flip over there, and then we're going to go through the hormones, and I want you guys to ask me any questions that you have, because this is pretty dense stuff, the endocrine system in general. So let's start with the posterior lobe, just because it's easier. So from there, you have your ADH being released. So ADH is the anti-diuretic hormone. And the anti-diuretic hormone does exactly what the name suggests. If I had diarrhea, I would be having what kind of stool? Very wet, right? Think diarrhea and think, I don't want it to be that wet. I want, the opposite would be constipation, but we don't want it to be constipated. So we're going to make sure that it's in a certain level, which is why we don't just pump it out with no idea of what we're doing. We're always trying to maintain this kidneys. So for instance, if we're looking at a part of your kidneys over here, this is a section of your nephron, and you have these long tubules. So tubule, just like arteriole, is a small tube. So the all part just means small. So within these long tubules, you have reabsorption of water, reabsorption of different minerals. And what ADH does is it gets secreted into these tubules and causes the reabsorption of more water. So without ADH, you'd just be having polyuria. You'd be peeing out everything that you drink. So you want to make sure that you retain the water, because water is going to make up about 65% of your body. So you want to make sure that that's always in the proper level. And when I say proper level, it's under osmoregulation. So your body's going to make sure that you have this specific level through osmoregulation. Okay, next up, we have oxytocin. So oxytocin is known as this cuddle drug, right? So it's what you get whenever you have skin-to-skin touch with someone else. It's also called the orgasm hormone. It's going to be what's released after orgasm, where you have a lot of touching happening, social interaction, and your body rewards you for that by releasing this oxytocin, which is going to actually combat stress, on a side note. So physically, though, what this oxytocin does is during labor, while you're about to give birth, it's going to be secreted into the uterus to create the smooth muscle contractions that would allow for the baby to actually be delivered. So very important for the uterine smooth muscles. Also, it's what's going to cause the actual ejection of the milk from the mammary glands. So you want to make sure that so the stimulation is, if you have suckling at the nipples, you're going to have prolactin being stimulated, which causes the production of more milk. And then the actual process of lactation will be stimulated by this oxytocin release. Also, the reason why mothers are so attached to their child whenever it's right after birth is this huge surge of oxytocin that's released at that moment. So this is very important for your childbearing and child rearing activities. So the connection that a mother has with this child is based partly or largely upon the release of this hormone and its actions. Okay, so next up, you have the intermediate lobe, which I said they didn't label before, but you see that the MSH, the melanocyte stimulating hormone, is going to be released from there. And what this does is trigger the melanocytes, the mature melanin secreting cells, to start to produce more of this pigment. Okay, so next up, you have these the follicle stimulating hormone, and you have the luteinizing hormone. So now both of these are going to be going to the gonads. So testes for the male, and it's going to go to the ovaries for the female. It's the same hormone, but it has different effects. So both of them will be triggered by the gonadotropic hormone. So you have the GnRH, which is going to lead to the stimulation of your FSH and your LH. So I'll write that down for you. So your GnRH, which is your gonadotropin releasing hormone. So that's going to be what causes, so it's going to target the gonads, and then it's going to cause the release of testosterone or estrogen and progesterone by your ovaries. So depending on where it's going to cause different things to happen. So, so you want to make sure that you realize what's the differences there. So if the follicle stimulating hormone, it targets your ovaries for a female, it's going to inhibit that production. And then you also have the luteinizing hormone, which does the same, but they have slightly different effects because your luteinizing hormone triggers the luteinization process. So once we get to a reproductive system, we'll get into more detail about that. Versus your follicle stimulating hormone is involved in, as the name suggests, the development of your follicle. Once again, once we get to the female reproductive system, we'll speak about that. Now, the luteinizing hormone and the follicle stimulating hormone for the male, some of it will be in charge of the production of testosterone, while others will be stimulating more sperm production. So spermatogenesis in males for FSH, and then ovarian follicles for the females. And then the luteinizing hormone, testosterone in males, ovulation in females. Okay, next you have your prolactin releasing hormone. So this is going to be PRL. Prolactin equals PRL. And so what prolactin is going to be doing is primarily stimulating the production of milk or lactation so that you would be able to breastfeed your child. Next up, we have our GH, our growth hormone. And so what the growth hormone does is basically it's going to affect your metabolic rate, and then it's going to affect the growth of bones and muscles in your body. So growth hormone, as the name suggests, is involved with your development. So whenever bodybuilders are trying to dope, they might be using steroids or growth hormones to be able to do that so that they can increase their age, which is going to be the thyroid stimulating hormone. And what the thyroid stimulating hormone does is trigger the release of and the synthesis of your T3 and the conversion of the T4 to the T3. So before we continue, let's talk a little bit about what these words mean. So T3 means that you have 3 iodines, and T4 has 4 iodines. So whenever you have a conversion between the two, it's going to be the transfer of an iodine off or on. So when you add an iodine to T3, it becomes T4. And if you remove an iodine from T4, it becomes T3. 3 is going to be, your T3 and T4 are both going to be involved in your metabolic rate. And so this is going to alter how you're going to be using glucose in your body, as well as glycogen and your fat stores. So all of that metabolic rate, how you burn your energy, which energy to burn, is going to be involved with your T3 and T4. And then you also are going to have, so that's you are going to have an active form and an inactive form. So your T3 is going to be your active form, and then your T4 is inactive. And whenever your body needs to activate more of this thyroid metabolism function, it will have this conversion happening. And so you have this transfer that leads to the conversion. So this can be seen on page 607. So you have the conversion between the T3 and T4, and then you're going to see how it changes there by having the iodine being removed or added. So, okay. So next up, we're going to be talking about, where are we? Next up, we have your ACTH. That's going to be your adrenocorticotropic hormone. Adreno means the adrenal glands. Cortical is going to be the cortex specifically. And then tropic means that it's going to stimulate those glands to secrete something else. So it's a tropic hormone. And so the adrenocorticotropic hormone is going to cause the release of cortisol from your adrenal cortex. And the way that we're going to remember that is cortisol has the same root word, the cort, as cortex. So your adrenal glands have a medulla in the middle, and it has a cortex on the outside. And each layer has a different secretion. So you have different glucocorticoids and minerals cortical minerals that are going to be released from the adrenal medulla and cortex. So in the cortex, you have one layer on the top. This is page 611, where you have 3 zones of your medulla. Of your cortex. And so this cortex, the outside layer, is going to have zona glomerulosa, which is on the topmost end. And then that's going to, and what aldosterone does in the kidneys is lead to the reabsorption of sodium so that you maintain balance. So then you have the zona fasciculata, and that's going to be involved in the release of cortisol. So the cortex releases cortisol. And then lastly, you have the zona reticularis. And then reticulum means a network. So these are going to be they're going to be stimulating they're going to be releasing androgens, which are going to be sexual hormones, so reproductive hormones. And then lastly, you have your adrenal medulla at the bottom layer, and this is at the middle of the adrenal glands. And what this is doing, I don't see a... all right, I was looking for a model to see if I could show you guys this in a better way. Yeah, I don't know how much this will help. But basically you have these layers. Let's see if this layers of the adrenal glands, where you have the cortex on the outside and then the medulla on the inside in the middle. And over here, we're talking about the middle being the one that's going to be secreting your epinephrine and your norepinephrine, both of which are going to be your fight or flight neurotransmitters. So if epinephrine and norepinephrine is released into the blood, it is an endocrine response. And then if it's released in between synapses, then it's going to be a nervous system response. In both cases, though, it's going to lead to your sympathetic innervation. So your heart rate's going to increase, your metabolic rate will increase, your pupils will dilate to let in more light. You need more, so you need more ATP. To get ATP, I need more glucose and oxygen. To get the glucose, I'm going to break down my fat reserves and my glycogen reserves to make more glucose. So these are going to be all triggered, all these effects, by your epinephrine and your norepinephrine, which is released by your kidneys. Not kidneys, your adrenal. Sorry. Okay, so that covers that whole diagram. And we also basically covered 602 and 603. Okay. So I have a question for you guys. Which of the two is the active form of your thyroid hormone? Is it the T3 or the T4? And basically, which one do you have more of? Okay, so we have one answer. No, no one else? So you're going to have the one that requires less iodine is actually your active form. So that's the one that we're going to use to increase cellular respiration, which is cellular respiration is this aerobic respiration where you have ATP production, and basically it's your metabolic rate. So both of them contain iodine, like we said, T3 and T4. The only difference is the number of iodine molecules that it has. If it is the T3, it only has 3. If it's the T4, it has 4. So, and the body is going to convert between the two in response to the needs of the body. And if it goes out of whack, then you can end up with T4, with your thyroid functioning being hyperthyroidism or hypothyroidism. So other than that, your thyroid is going to produce calcitonin, which is going to lower the levels of calcium in your blood, and it's going to instead move it from the blood to the bones, right? So the calcium that we need to build up our bones, give them their compressional strength, is going to come from the blood. So we have this homeostasis between the blood levels of calcium and the bone level. If you have calcitonin, calcium will be in the bone. And then if it's the parathyroid hormone, that's going to take calcium off of the bones and put it into the blood. So if you have too much of this parathyroid hormone, what would happen to the strength of your bones? That was a question for you guys. Right. So calcitonin means that you're taking the calcium from your blood and putting it into your bone. So it would be released in response to what? Why would you want to put your calcium into your bones? What's the level of the calcium in your blood if that's happening? Okay, I'm assuming Brianna no longer wants to participate and no one else wanted to say anything. So you're going to have the calcitonin, whenever the blood calcium levels are too high or high enough, your blood is going to take your body's going to use this hormone action to take the calcium from the blood and deposit it into the bone. And so that's going to build up the bones. And then if you have too much parathyroid hormone, it's because you have too little blood calcium levels. So the lack of blood calcium triggers the breakdown of your bones, which are made of calcium, to increase the blood calcium levels. So there is a homeostasis there a balance that exists for your blood calcium levels, where if they are too low, parathyroid hormone comes in and causes an increase by removing the calcium from your bones and putting it back into the blood. And then if it is too high, it is going to take the calcium from the blood and put it into the bones. So whenever they tell you guys that if you don't have that you should drink milk to build up your bones, and you know that whole got milk commercial, what they're referring to is the calcium that's found in the milk that would increase your blood calcium levels and lead to your body producing more of this calcitonin, and therefore putting those calcium into your bones. But now this calcitonin will not operate if you don't have it activated by the kidneys. So the kidneys have this vitamin D3 that is necessary for the absorption of calcium from your diet. So if you don't have vitamin D from the sun or from a supplement, and you're sitting there and you're drinking milk and you're taking calcium, you could take a lot of it and you actually will not have the benefits of absorbing more calcium, because you don't have the vitamin D activating calcitonin to lead it to do that. Okay, so that's it for the whole relationship there. But this is actually important to point out. So if the thyroid gland, if the calcitonin does that and the parathyroid does the opposite, these opposite effects that antagonize each other. And that whole explanation of what I just said with the opposite effects, that you can see on page 609. Normal blood calcium range being between 8.5 to 11 milligrams per deciliter. And then your body is going to respond to the calcium levels by secreting either hormone. Okay, we already went through 610 and 611. So you have your 3 different hormones being released from the cortex. Each layer of your cortex has a different, or zone, has a different hormone that gets released from there. So on the topmost layer of your cortex, you have your mineral corticoids, such as aldosterone, important for your salt retention, which is going to be where you have your cortisol being released. And this is going to be to also impact how you store your fat and your energy. So it impacts your metabolism. Okay, great. Okay, then you have the zona reticularis, where you have your sex hormones once again. So these are your androgens. And lastly, the adrenal medulla, which is the epinephrine and norepinephrine. So the medulla, the middle of your adrenal glands, are going to be secreting these sympathetic innervation hormones. Okay, now let's get to one of my favorites, your pancreas. So the pancreas has both paracrine and endocrine functions. And we're only going to talk about the endocrine ones right now. For the paracrine, we're going to be talking about that once we get to your, and exocrine rather. Well, so both of them, we'll be talking about that once we get to your digestive system. So like we said before, you have your alpha cells, and these alpha cells of your pancreas, they secrete glucagon. Glucagon is going to cause the blood glucose level to increase. Your beta cells are going to produce insulin, and insulin will cause the blood glucose levels to decrease. Now, my question to you is, how does that happen? How does insulin cause your blood glucose level to decrease? How does insulin change the glucose levels? Because we know how glucagon is doing it. It's taking this polymer of glucose, this glycogen, and breaking it down back into glucose. Because we put all of our glucose into this one storage unit, right? So think about how messy it would be to be walking around with all these napkins, not in this little box, but everywhere. It'd get very clustered. So we take our glucose and we put it into this one organized place, and this altogether is our glycogen. So as soon as we need more glucose, we go back to our liver where we have most of our glycogen stores, and we break down the glycogen and start making these glucose that we need. So if we have too much, we package it. If we have too little, we break it down. So now what about the insulin? How is that actually working? What breaks it down? I'm sorry, Yvonne, what do you mean? What's it? No, so insulin isn't going to, so glucose doesn't become ATP on its own, right? It has to go through aerobic respiration, right? So insulin doesn't break down the glucose. Instead, what's happening is that, remember how I told you guys that your cell has this membrane, it doesn't allow things to just cross over for no reason. So your glucose, this big molecule, tries to cross over the membrane, and it can't. It can't come in. It's too big to slip through the little holes of your membrane, right? So it can't go in because it's too big. So instead, you have an insulin receptor that's going to be on your cell, and what happens is the insulin binds to the receptor, causing a glucose transporter, GLUT4, GLUT4, like your glutes. Your GLUT4 is your glucose transporter, and it's going to pull in the glucose across the membrane. So now the glucose went from being in your blood to being where? So Yvonne, where did it go now? Yeah, sure. So insulin binds to the insulin receptor, causing glucose transporter, GLUT4, to grab this huge glucose and pull it in. So now, where is the glucose? It's not in the blood, it's in the... No, so your insulin is going to be released from the pancreas and go to everywhere in your body. Almost every cell in your body has an insulin receptor. And this insulin receptor allows for insulin to bind to it. It's a lock and key kind of thing. So it wouldn't go to the liver specifically, no. So it's going to go everywhere. You're thinking about the glucagon going to the liver. Because the glycogen is in the liver, and the glycogen is like this tissue box. Glycogen is just many, many glucose packaged together. So whenever you need more blood glucose, your glycogen is going to go in, and then it's going to start breaking this down to become the individual glucoses. Here's a little blood glucose for you. Here's a little blood glucose for you. Right? But that's what glucagon does. What about insulin? Insulin is triggering the cells to do what with the glucose? Use it. Okay, that's a good word. So glucose utilization, the ability to bring glucose into the cell and then use it for the aerobic respiration of your cell, that's going to be dependent on the glucose actually crossing from the blood into the cell. Because think about it, this glucose could be going in your blood the entire time, and if you have diabetes, for instance, and you have diabetes type 2, you are going to have insulin resistance, meaning here for months, they don't want to hear it anymore. So they're going to build this tolerance. And so because of that, they're going to, much like I'm coming into your ears, I just noticed. Is this still? Sorry, guys. So maybe that's a little too low now. Is that better? So whenever you have your insulin traveling through your blood, it any cell's receptor. Because each of your cells has a receptor for this. And once it does, it's going to cause the glucose to be pulled from the blood into your cell. If you have diabetes type 2, which is insulin resistance, or characterized by that primarily, your body's insulin receptors no longer react to the insulin that's in your blood, which means that your cells don't get the glucose that they need because your cell never gets the signal to send out its GLUT4 and grab it. Does that make sense? Nope. No answers. Yes, no. Anyone? All right, I'll just keep going. You tell me if... No, I was just asking, does that make sense? That's what I was asking. I'm saying if you have this, the cell, and it has an insulin receptor on it, and every cell pretty much in your body has an insulin receptor on the membrane. And once the insulin binds, it causes glucose to go from blood to the inside of the cell, and therefore the cell can use it. So your cells need energy. In diabetes type 2, your body isn't able to pull in the glucose because you have insulin resistance. So what that means is that you're going to have the insulin hit the receptor so many times because your blood glucose levels are so high always. Okay, so because it's always happening, your receptors stop responding. They're like, I don't care if you have insulin. I'm not going to respond. You keep telling me to do this over and over again. I need a break. So just like listening to loud music always leads to the receptors in your ear to stop taking in the signal and you stop hearing as much, the same thing happens for your cells, where because of the insulin receptors getting this resistance, you no longer have glucose being pulled into the cell, and therefore cells are not eating. So it stays in the blood, and it just gets worse and worse until you start having to have amputations where you're missing fingers and toes, anything in your periphery because it's not actually entering the cell, not because you don't have enough of it. So a similar problem happens for diabetes type 1. So in diabetes, immune response that leads to the destruction. So autoimmune, what does that mean? So you have a response of your immune system to yourself. It's an autoimmune response. And when this happens, your body attacks the beta cells that are producing the insulin in your pancreas and causes their destruction, which means that you do not have insulin being produced because you do not have beta cells. Is that clear? Okay, so in type 1 diabetes, you have no beta cells making insulin. So no insulin means nothing to touch the receptors, which means glucose just keeps going up in your blood, but not in your cells where they need it. Now, in type 2 diabetes, you have high blood glucose levels because every time you eat and you break down those carbohydrates from whatever you just ate, your insulin levels go up so that you could take the blood from the glucose from your blood and put it into the cells to use. So now in type 2 diabetes, once again, you have such a high level of glucose in your blood always that you always have insulin being produced, so that your receptors always have this reception happening to the point where they develop resistance or a tolerance. And that's the point where your body stops responding to the insulin that's in your blood, and therefore the blood glucose level continues to rise, and it's going to be toxic. Okay, so now you have different diseases that you're expected to understand. I'm assuming from multiple choice questions, where you have hyper or hypo production of these different hormones. And this is going to be summarized in the page 623. I don't know if he's going to specifically ask questions about that, but I would recommend that you take a look at that page and look at the description that they have there. So let's see. Is there anything that we still did not cover? Okay. All right. So from doing the questions that you guys had to do for this review, which questions stood out as something that you still don't understand that you wish you did? So what questions do you have for me that I can help you to understand better, or anything that I haven't covered so far? Anyone? Anyone at all? Okay. So what I'm going to do is, I guess, wait, you have a question? 120. I don't know what question that is. Can you tell me, can you explain to me what they're saying in that? I'm waiting for the response, and then if not, I'm just gonna end it off here. So my question is, what is an additive effect? It asks two hormones that has additive effects are called. So the question is, what is an additive effect? Okay. So if you go to page 617 of your book, you're going to see that there's a chart where you have antagonistic effects, additive effects, permissive effects, and integrative effects. So okay. So are you looking at that page, or should I just describe it to you? The GAS stress response. Okay. GAS. Do you mean the Ross system? Or is this something that I don't know? So physically have the first edition. So the pages are different. Okay. So this is one of the last modules there, but you basically have these different types of effects that can happen when you have hormones being mixed. So if you have multiple hormones acting on something at the same time. So if both the hormones if they're antagonistic, like let's say insulin and glucagon, or let's say calcitonin and parathyroid hormone. These two have antagonistic or opposing effects. So the bones puts them back into the blood. So they're antagonistic. So then you have additive effects where you're going to have two hormones that do the same thing. They have the same reaction or effect. So the example that they give over here is the growth hormone added to the glucocorticoids. So the glucocorticoids, those would be your steroid, your glucocorticoids. Those are going to be your cortisol, which is going to be a steroid derivative. And what's going to happen is that if both of these hormones are acting simultaneously, they both add to each other. Okay, then you have the permissive effect, where one hormone will not respond unless it. So you need one thing to happen to lead to the other thing. It needs permission. And then you have the integrative effect, where you have different hormones binding to different protein receptors and causing entirely different cascades that integrate with each other. So this is going to be an integration of the two effects in order to create this one larger effect that's made up of the sum of those two. All right, so Brianna, let me know if that helps. I don't know what the choices are, but maybe I can help you more if I knew the choices. Matthew, so are you talking about the RAS, R-A-S, or did you actually mean G-A-S? general adaptation syndrome. These are the stress response. The resistance phase. Okay. Yeah. So basically, let me lower this so that I can sit and talk to you. That should work, right? Okay, awesome. Okay, so you have 3 different phases of your. One second. I copied the question into the chat. There's a short answer about that for the review, so I was just hoping you could review it. Of course I can. Yeah, man. Also, so for endocrine, those questions they're already in the Anki card, and actually in like 2 minutes I'll show you how you can go through the Anki cards to look for the answer, so that you would be able to have the answers even to the short answers. Okay, and now just to answer Brianna's questions before I get into GAS. So the choices are agonistic, antagonistic, synergist, cofactors, and permissive. And the question was asking if it asks 2 hormones that have additive effects are going to be called. So this would be a synergist. So a synergist is going to, or actually, would it be agonistic? I'm like 99.9% that it should be your synergist, but it could be agonist. One moment, I will check and give you the final answer. But that's funny. That's a little bit tricky to figure out. All right, you know what? I'm going to show you guys how to do that, what I just said about the Anki thing. I'll show you that right now. No, so antagonistic is opposing, but agonistic is going to be together. Synergistic is better because synergy means that 2 things are going to add together to create a synergy. So that's the additive kind of effect. Versus agonist would be like only one, usually. So like you have agonist muscles, like your biceps in this case would be an agonist in the bicep curl. You have an antagonist muscle, which is the tricep, which is not being stimulated. But the bicep might have another, which is the agonist, might be working synergistically with your forearm muscles to create that flexion. So I'm pretty sure that it should be synergy. Just 1 second, guys. I'm getting the connection over here so that I can show you guys this part. Okay. So where's the HDMI? Come on. Huh. Interesting. Just 1 second, guys. I'm making sure that I could share this screen with you. Okay. What about now? Nope. Scaled. Faster display. Okay. Bingo. Nice. And let me switch over. I have this invisible box that I can't move. Really? Okay, guys, so it might get a little bit weird just because of what I'm seeing over here is happening. But let me switch over to the HDMI, and then I'm going to keep my mic on this time so that you guys could hear me. So now, by going over here, I'm clicking. So the first thing that I want to do is open up Anki. I have this invisible barrier here that I'm not allowed to cross for some reason. So I'm going to go to applications and go to Anki right there. So now I open it up and boom, this is what comes up. So now from here, I'm able to click on browse. And please let me know if you guys are following me or if you need me to do anything again. So once you click browse, you get this pop up over here. So you could click on whole collection, and now you could literally search the question that you wanted to ask. So for instance, we were just asking about the additive effects, right? So describe the 4 patterns of hormonal interaction. In general, the effects of the natriuretic peptides are blank. 2 hormones that have additive effects are also called synergists. So yeah, we were absolutely right when we were saying before. So if they work together and they're additive, they are going to be synergistic. So now I'm going to go to the general adaptation response. And then here's the short answer. Okay, so I'm just gonna switch over right now. I'm gonna unplug this so that we could go back to me reading what you're saying. Okay. And okay. So did you guys understand how you would be able to look that up? And Brianna, just to again answer your question, it's going to be synergist because whenever you have a synergetic effect, so like if you ever work for a company and they're being corny and they're like, oh, we need some more synergy in the room. What they're trying to say is that they want people to work together to create something. So they want people to add their efforts. So that's what they mean there by synergistic. Okay. And then Matthew, so what happens to you? You're eating your food, and in the middle of eating your food, you look over, cheetah. Okay. So now I see the cheetah and I act quickly. So I need to innervate my sympathetic nervous system in order to. Sympathetic nervous system is going to be basically controlled by your epinephrine and your norepinephrine. So the primary neurotransmitter used by a sympathetic nervous system are those that I just said. So what your body's going to do is initially you're going to need more of this. So in this first stage, it's going to send the signal. so the middle of your adrenal glands, to secrete your epinephrine and norepinephrine. I'm sorry, 1 second, guys. Yo. Yeah, are you downstairs? Okay. I'm right. What? Okay. I got you. I got you. Okay. Just let me know. Yeah, I'll see you in a couple minutes. All right, bye. Sorry about that, guys. That's my ride. So I'm definitely have to pick up his phone call. So in this general adaptation syndrome, GAS, you're going to have the first part is your alarm or flight or flight stage. And in this case, your body instantly wants to increase the mental alertness and start to have this sympathetic effect happen. And the way that our body does this is by its primary neurotransmitter for this, which is epinephrine and which is adrenaline. So you ever hear the thing, oh, the adrenaline was pumping? That means that your epinephrine was being secreted. So where is it being secreted from? From the middle of your adrenal glands, your adrenal medulla. So these are short-term kinds of changes. And in response to these changes, you're going to have a phase of resistance where you have cortisol being released. And what cortisol does is basically, and the rest of the glucocorticoids, is basically start to change the way that your body is using its energy so that you would be able to sustain this response. So it's going to start off with your energy reserves being used. So your fat is going to be broken down. You are going to have amino acids being released into the muscles because your muscles are going to need those